Well, good morning, everyone. Welcome to the Hydrogeophysical Methods for Groundwater Evaluation, Management, and Modeling. My name is John Lane, your assistant chair. My co-chair is Esmond Akin from Aarhus University, who unfortunately could not join us. So I'll be running this solo. Our first speaker of the morning is Jeff Kennedy from the USGS. He will be speaking to us about non-invasive water table imaging with joint DC resistivity, microgravity, and hydrologic model inversion.
All right.
Jeff Kennedy. Good morning, Jeff.
Thanks, John. Thanks, everybody, for coming out this morning. I think it's a real honor to give the first talk at AGU. At least that's what I tell myself. Today I'm going to be talking about some work using ERT and time-lapse gravity with some hydrologic modeling. The conceptual basis for this is that with ERT we get these nice high spatial resolution images, but there's not a lot of quantitative information for hydrologic modeling. We need to convert resistivity to some property of interest like water content. On the other hand, gravity in a lot of ways is sort of the ultimate quantitative measurement for hydrology. In most cases we use the Bouguer slab approximation there, which is just a linear relation between a change in gravity and a change in one-dimensional water stores. There's no consideration of depth to water or porosity. It essentially works in all cases, but there's no depth resolution whatsoever. Joint inversion, by that I just mean combining multiple methods. I don't have some brilliant new analytical solution for this. It's really an empirical look at the effect of these different data types on model calibration. As far as joint inversion, there's lots of examples, more and more all the time. Gravity and magnetic resonance sounding. Nice recent example in WRR using gravity and hydraulic tomography, various combinations with ERT, etc. This study, in addition to joint inversion, also uses what we call coupled hydrogeophysical inversion. And by that I simply mean putting the geophysical forward model on sort of the same footing as the hydrologic model. So from our hydrologic model, we predict the geophysical data, whether it's resistivity or something else, through a petrophysical model. And then we have a model misfit between the geophysical data and a model misfit between the hydrologic data we can use to update our model parameters. A lot of this work comes out of the efforts by Ty Ferre and his students at the University of Arizona. I'm going to be demonstrating this method with a case study from the Colorado River Delta in the southwestern U.S. There's been a great deal of effort here in the recent years to reestablish riparian vegetation. Because of upstream dams, essentially the whole delta has no flowing surface water except in a very few locations. Restoration efforts include both these passive sites like you see here and actively managed sites where there's been vegetation clearing and trenching, etc. But the question really is what type of flows. There's a great deal of flexibility to design flows in the channel, and we want to know what type of flows provide the best growing conditions for riparian vegetation. We can have high peaks with quick recessions, lower peaks with longer recessions, and underlying that question is the question of whether geophysics can improve the hydrologic models that are used to predict these riparian growing conditions. Quick look at the study area. Again, it's in southwest Arizona. The river here forms the US-Mexico border, which creates some interesting logistical challenges. But in this kind of poor oblique image there, you see the river going from left to right. This particular scene has water in the river, but 99% of the time it's completely dry. If we look at a cutaway view of that same scene, we can see the configuration of our data collection. We have a single ERT transect parallel to flow, not perpendicular, but parallel. Our ERT data, the inversions look like this. Over the course of a week during this flow in 2014, the channel's dry. We get a single peaked hydrographs, and the channel goes back to dry after about 6 weeks. During the first week of this flow, our ERT goes from top to bottom, and we very clearly see this rising water table in the data. This is a little bit off the channel, so there's no land surface infiltration. It's just a rising water table. The repeat microgravity data consisted of 6 stations, and this transect is perpendicular to flow. So the resistivity and the gravity are perpendicular to each other. Again, 6 stations. A combination of absolute and relative gravity data. This is an A10 absolute gravity meter and a Burris relative gravity meter there. We did 3 surveys. and before the flow, one after a week and one after about 3 weeks. So the blue line is after 1 week, so we see a nice large increase in gravity at the channel, essentially zero change away from the channel. After 3 weeks, we see a smaller, the change is decreased a little bit at the channel, but then across the board increase at all stations after 3 weeks. And finally, we have a monitoring well located about 180 meters from the channel, where we recorded a nice distinct, about a 3-meter water level rise during this flow event, followed by a steady decrease. The modeling I've done uses Hydrogeophysical, which solves Richard's equation both in the saturated and unsaturated zone. This animation shows infiltration and drainage over about a 30-day period. This particular model is using the Brooks-Corey relation between saturation and hydraulic conductivity. Specified flux boundary here on the left, just some arrows pointing out where the data are collected relative to the model. And finally, the prediction of interest for riparian recruitment or germination depends on depth to water and water content at 50 centimeters depth at the channel. So not at the location of our monitoring well or really of any of our geophysics, but right at the edge of the channel there. Using a Markov chain Monte Carlo method for parameter identification. This is a Bayesian method that relies on a large number of model runs to identify the posterior parameter distribution using the DREAM algorithm by Jasper Vroot. A 1D parameter sensitivity analysis really indicates, not surprisingly, that specific yield, hydraulic conductivity, and the Brooks-Corey exponent on the bottom there are really the important parameters in this case, a fairly simple model. These others are conductivity, poor conductivity, beta is part of the Brooks-Corey exponent, and then air admittance pressure essentially have zero effect in this context. The objective function for resistivity, I think this is a little bit unique. I'd be interested to hear of other examples. Basically, we're extracting a 1D profile of water content from the hydrologic model at the distance of the resistivity transect. We convert that water content profile to a resistivity profile using Archie's law, just an exponential relation between the two. Then we extrapolate the 1D profile to a 2D cross-section and then difference that simulated resistivity with the measured resistivity to get some sort of error matrix. Then it's just a matter of squaring and summing each terms in the error matrix and repeating that and summing for each of the 7 ERT profiles. So we get a single objective function for the ERT. Gravity is easier. We just use Newton's law relative to each cell and each gravimeter position with the simulated mass change in each cell. So we have a predicted time series. We can use a sum of squared differences with the observed time series. So looking at the results, if we just use gravity, we get posterior parameter distributions that are seem to be well behaved. They're well within the parameter bounds. On the bottom here, we see in color the observed versus the simulated. The shaded gray curves are the family of posterior distributions instead of a single best fit model. With this method, we get a family of acceptable models. So a decent fit there, I guess. On the right then are our prediction of interest. The left plot shows the depth to water, again, adjacent to the channel. And on the right, we see saturation at 50 centimeters depth. On the bottom, these histograms show the distribution at day 30. So at the right edge of this upper plot, this is the distribution of the acceptable models. And again, the colored models here indicate accepted ones. The shaded ones indicate sort of the range of predictions that are possible from the model. So reasonable output from this, we get a fairly well-constrained depth to water, around 3.9 meters. Less constraint on the saturation, a fairly broad range between 0.2 and 0.6 with a peak around maybe 0.58. If we look at resistivity alone, we see something different with the posterior parameter distributions. Now these variables are all skewed to the edge of their a priori range. The prior in this case is a uniform distribution between the axis limits you see there. A and B are the coefficient and exponent of Archie's law. So the resistivity alone doesn't seem to be effective in constraining these parameters. nonetheless, if we look at our predictions of interest, they're actually not that much different than than indicated by the gravity data. We see a slightly deeper predicted depth to water. Instead of about a peak at 3.9, it's 4.3. Saturation is similar. Just looking at these plots, it seems like it's more well constrained, but it's not necessarily a good estimate. Now, if we combine gravity and resistivity, we see something that's effectively about the same as gravity alone as far as the parameter distributions. I think it's kind of interesting that the Archie's law exponents sort of removes we get a much different estimate than we get from the resistivity alone. The predictions of interest, again, with depth to water and saturation, fairly similar between the two methods. Not a lot of difference there. And finally, we can look at just using head for model calibration. Again, this monitoring well is 180 meters from the channel. We get this weird bimodal saturated conductivity behavior. Specific yield is essentially the same as gravity. And the Brooks-Corey exponent is actually on the opposite edge of its range. The observed in dark black versus the simulated, a reasonable fit. And this bimodal distribution is really reflected in the predicted depth to water. So in this particular case, I'd argue that this groundwater level record is not very effective for calibration, probably mostly because it's so far from the channel. If we compare these predictions of interest using either gravity alone, ERT alone, or combined, we get pretty similar predictions of interest. With head, we get something pretty completely different. So in conclusion, as I just mentioned, either method alone leads to similar results, but different than using groundwater data. I think most importantly, the model was run with a fixed depth to water prior to infiltration. The depth to water was fixed. And that's probably where the ERT would be most useful. That's where we can see that depth to water. So I really need to repeat this with that as a variable parameter, I think, to really explore the value of the ERT. Importantly, I think, even though the gravity and ERT led to similar predictions, the model parameters were quite a bit different, which I think would have important implications under different boundary conditions. If we want to simulate a different flow event, those different parameter estimates are likely going to lead to different output. And finally, we would be better off with a specified head boundary instead of a specified flux boundary, so we can predict the effect of different flow events. This data has been published as a data release and an open file report if you want to jot those down, or feel free to drop me an email if you'd like to discuss further. Thank you.
Thanks, Jeff. Hey, we do have time for questions. Any questions? Jeff, I have one. So, how do you think how much value did you think the ERT added, and would you do this differently?
I think not necessarily the data collection. I'd be tempted to do a perpendicular transect instead of a parallel transect, because essentially we're measuring one 1D profile, even though we have the full profile. But I think there's probably more details in the modeling. I'd work more on the modeling before I changed up the field data collection.
Okay, all right. Any other questions? Okay.
Thank you.
Thanks, Jeff.
Yep. I have 15 minutes, right?
Yes.
Okay.
We gotta wait just 2 minutes before we
Okay.
can start. So. Okay.
May I start now? No, I have to wait for 2 minutes. Okay.
AG's asked us to stick to the schedule, so we're going to wait 1 minute before we get started. But while we're waiting, I'll introduce our next speaker. Is Yano, and he'll be talking to us about estimation of groundwater recharge in a Japanese headwater area by intensive collaboration of field surveys and modeling work. Yano. And
Can I start? Okay. Good morning, everyone. I'm very glad to have my presentation today in the very first session of this year's AG4 meeting. And in this study, we try to understand the local water cycle deeply in order to estimate groundwater recharge rate in Japanese mountain sites. Yeah, let's get started. Actually, Suntory is a beverage company in Japan, and we use huge amount of groundwater for manufacturing our products. So we think we have to know the groundwater recharge rate because it is the water input for our water source. And actually, there are a lot of cases or activities of water conservation. So they have to know these kind of activities are good things for groundwater or not. Groundwater recharge rate is very important for them and for us. But unfortunately, we think there are several methods for estimating groundwater recharge rate, but we think no methods established to estimate groundwater recharge rate in arbitrary areas and time scales. Basically, the groundwater has an element that goes to the deep layers or seas directly, but that kind of elements are often excluded from the assessment. So, in this study, we try to estimate groundwater recharge rate by understanding local water cycle deeply and develop a hydrological model. And in future, we want to apply this method to different basins to be the generalized method. And this is the study area in this study, the Jinggu River in Yamanashi Prefecture, Japan. And this is a concept of our study. We collect the true or real value, such as topology, geology, or river runoff or something from the actual field, and we reflect these field data into the model. And model can estimate invisible parts like groundwater recharge rate or groundwater flows. And this study is not the one path process, so we got some feedbacks from the model to gather the additional and effective field data. And we call this cycle as dialogue between field survey and model works. And we adapted the GET flows model, which is developed by the Japanese ventures. Here is the research step. And at first, we tried to develop a model only by the existing literature, especially in the geological structure and climate data. And we calculated the water cycle, and we validated the field data, validated the calculated data with the field data like river runoff and groundwater level and springs. And we decided the accuracy is enough or not for estimating groundwater. And if not, we get back to the field survey to check or to confirm the important points, especially in the geological structure. And here is the typical field data obtained through the arrow. So, yep. And on the left-hand side, we shows the geological structure. And sorry, it is not so clear, but here are the kind of pink lines, which shows the lineament. And in this area, there are a lot of lineaments from the areas photographs. And the red line shows the fault. And in this area, lineaments showed very higher permeability from the field survey. So we set the permeability like this, and fault is has less permeability groundwater flows. And on the right-hand side, I show the soil distribution in this area. This area is mountainside, so there are a lot of types of soil layers, thick and thin, and high permeability and low permeabilities. Yeah, and this is the developed model. The left shows the original one, which was developed by only from existing literature. It is kind of simple. And after the field data, actually we had 4 times of field data for 4 years. And we reflected that kind of lineaments or soil layers or something, some field data to the model, and the model got a kind of complicated, and yeah, and a lot of parameters and a lot of categories, and of course each categories has each parameters of the groundwater permeability. And this is the result of the calculated groundwater level. On the left-hand side is the kind of original one. And there were difference between the observed and calculated data. So the black line shows the observed and gray one is calculated one. And there are differences between them in variation, time variation, and the observed value of groundwater. But after reflecting the results of field survey, it got better, we think. The both variation pattern, difference in variation and difference in absolute value improved, we think. And this is the result of the groundwater and surface water flow on left-hand side, and this is the recharge rate from each grid. So groundwater input from each grid. And the light blue line shows groundwater flows, and blue line shows surface water. And this figure suggests that the inflow of groundwater from outside, from the next watershed along the lineaments. This kind of line shows the lineament around this area. And yeah, so we can assess we can know the local water cycle, and we can assess the groundwater recharge rate from each grid. But here, we thought there is the potential for overestimation. And this pink color shows the grid with groundwater recharge rate greater than the local annual rainfall. It's of course possible, but this is also possible, we think. And in the riverbed, recharge and discharge water can occur continuously. So in this figure, we count the groundwater recharge 3 times, 1, 2, 3. So this might be the reason of the overestimation. So we removed this kind of grids by having a threshold of the water existence and water flows. So this is the removing results of overestimation. And in this area, there are not so very big difference between each kind of series, but yeah. And as a result, we assessed that around 65% of annual precipitation goes to the local groundwater. So go through the local groundwater level by the modeling. Yeah, and this is the summary and future work. We adapted the dialogue between field survey and modeling to understand local water cycle, and we could estimate groundwater recharge rate, which is invisible for us. In future, we want to validate this model by water quality and water temperature or mean residence time of groundwater. And after that, we would like to, as I mentioned before, we would like to develop this method as a generalized method for estimating groundwater recharge rate. This is just a kind of local model, so we have to expand to the other case. And by doing so, we can, of course, we can select the protection area, or we can contribute to these kind of several activities related to water conservation. So we want to contribute to sustainable groundwater use by forest management or forest preservation or something. Yeah, that's it. Thank you very much.
Yeah, we have plenty of time for questions. Please.
How did you calculate the unsaturated?
Unsaturated. Yeah. Actually, yeah. We adapted the model called get flows, which is shows the general purpose generator flood fluid flow simulator, which was developed by the Japanese researcher, and the unsaturated and saturated zone is installed in the model, so we can assess the both of water flow in one package, I think. So that is the function of the model. We can assess it in this one model. Yeah.
Any other questions?
Were there any other estimates of recharge you could compare your results to?
I'm sorry?
Were there any other estimates of recharge besides the model?
You mean the other elements other than groundwater recharge rate, right? Or other sites or other regions? Sorry, I couldn't catch what you mean.
You have a modeled prediction of recharge from your model.
Mm-hmm.
Are there any field measurements to compare your model to
Oh yeah.
other models?
Yes, I assessed. We assessed here is the groundwater level, and we validated the runoff, river runoff along the sites and the points of the springs. Yeah, that they are the validated data, but we maybe I think it is not so enough for estimating the accuracy of the model, so we have to improve it.
So I have a couple of questions.
Yes.
One, you mentioned airborne laser scanning. Was this LiDAR that you were using?
Yes, we use the LiDAR data, the very kind of high resolution topology. So, yep, but yes, I.
Okay, that was the first question. And then, so your original model that was based in the literature did not calibrate well, poorly calibrated.
Yeah.
But the model based on this additional information was quite improved. What was do you have any? Can you give us any insight of what data that you collected was the most important for that improvement?
Yeah. Actually, we don't quantify each contribution, but in the original one, the water is lack. So water doesn't enough. Water volume is enough, but the water have to be installed from the next watershed. So we think the very important point is the linear means, because it can bring the groundwater from the neighbor watershed, I think. So in this study, the observing linear means and set the characters of linear means are very important, I think.
Okay, so the original model did not incorporate the limits?
Did not.
I see. Okay. All right, do I have any other questions? Thank you.
Thank you very much.
Unfortunately, our next speaker at 8:30 withdrew, so we're going to take a recess until 8:45 when we'll start up again. And Mr. Pandey, are you in the room? or Pandey? That's a problem. That's our next speaker. They'll start up again at 8:45. Okay, well, folks, well, thank you for your patience. Our next speaker is Emily Maher. She's going to be speaking to us about geophysical surveys of the hydrologic basin underlying Yosemite Valley, California. Emily Maher, welcome.
Hi, like he said before, my name is Emily Maher. I'm from the University of Nevada, Reno. My talk today is going to be on the geophysical surveys of the hydrologic basin underlying Yosemite Valley, California, that we conducted this past year. I would like to give a shout out to the National Park Service for letting us get a research permit and conduct this study. I have a special thanks to Kelly Shaw and Dr. John Louie at the University of Nevada, Reno. They helped immensely in preparing this talk and conducting this research. And also a thanks to the Yosemite National Park geologist, Greg Stock, who provided a great amount of insight and information on what we were doing. On here, you can see, if no one knows exactly where Yosemite National Park is in California, it's about in the middle. So the motivation for this study was to find the depth to bedrock. It has been yet to be determined the maximum depth within the valley. By doing different geophysical surveys, it could give us a better understanding of what the groundwater hydrology looks like. In 2011, Nicholas Newcomb and Graham Fogg from UC Davis did a study to model the groundwater hydrology in order to determine the effects of groundwater pumping within the valley. This is because during peak season, the Yosemite National Park gets over 3.7 million visitors, and in one day, 700,000 gallons of water can be pumped from their 3 main wells just in one day. So the only other prior geophysical work to find the depth to bedrock within Yosemite Valley was done in the mid-1930s by Benno Gutenberg and his team. They did reflection and refraction methods using 4 to 14 oil-dampened variable reluctance electromagnetic seismometers. And with that, they created this contour map. And the red on the outside show their shallowest assumed depths, which is 200 meters. And then as you move more to the eastern part of the valley, over here you get they predicted about 600 meters depth, and that is over kind of by the Ahwahnee Hotel. So the methods that we conducted, we did 2 different shallow methods and 2 different deep methods. Our shallow methods were resistivity, shallow REMI, and then the deeper methods to go below 30 meters were gravity and deep REMI. The resistivity arrays that we did, they were 94 meters long, and they had a maximum of 31.6 meter A spacing. The shallow REMI methods, we used 88 meter long arrays, and then to evaluate the data, we used VScope and SizeOpt for the processing. We used a Lacoste and Romberg G509 relative gravimeter to get our gravity readings, and then to do our inner terrain corrections, we used a less than 1 kilometer distance from a 1 meter resolution LiDAR. The deep REMI method that we performed, we did 4 different transects with 27 to 30 Texans. These transects were about 1 meter long. The Texans were provided to us from NSF-supported IRS Pascal Instrument Center at New Mexico Tech. So here's a map of all our different transects. We did one from the base of El Capitan down. All these are north-south because the valley runs east to west. So for deep REMI, we did a transect at El Cap. We did a transect from Yosemite Falls down, one at Housekeeping and North Pines. So our deep methods were performed at all 4 of those. And then our shallow methods were only performed at El Cap, Yosemite Falls, and Housekeeping. Our shallow results yielded low shear velocities for the upper layers. So a low shear velocity in this area would be less than 200 meters per second, and then for the resistivity, it would be about 100 ohm meters. Both of these attributes are associated with clay that come from till and glacial clay beds, glacial lake beds. When you find the area of your clay, you're gonna have to subtract that from the area of the aquifer, just because it's taking up area in there. So Gutenberg also did a ground roll velocity when he was doing his different reflection and refraction, and our transects match up with that, with his. So if you look at we have the depth below ground surface right here. In the higher layers, our velocities are lower. So it goes from like 0 to 500 meters per second for our shear velocities, and they're all relatively below 500, and Gutenberg's assumptions for ground roll velocity were a max of 275. If we also look at our different resistivity, the red color shows high resistivity, and when you move down to like green and blue, it shows low resistivity. And where a lot of the times our shear velocity changed, you also had some sort of change in your resistivity. For the different resistivity and shallow Remy, the talus, so closer to the profile on the sides, which would be where like the cliff faces are, talus has higher shear velocities and higher resistivities, and you can kind of see that on this transect especially, it matches up pretty well. You have a pretty dark red, and then you have a very low shear velocity, and then it changes as you would move farther down. And then as you move closer to the middle of the valley, you'll have like a sandy fluvial outwash, which creates a quicker shear velocity, and then you'd still have your higher resistivities, which is shown with the yellow. So for our gravity, the one thing we have to keep in mind with the different methods is that our terrain corrections are very large. As you can see, the total terrain correction up to the right of your screen, it essentially matches our latitude versus our total terrain correction, matched our latitude versus our complete Bouguer anomaly. And that's because of the cliffs and everything, it's essentially the same as the basin anomaly. So our less than 1 kilometer terrain corrections, like I said before, we used a high resolution local LiDAR, and then as we got out to greater than 1 kilometer, we used a 30-second Gtopo 30 DEM file. So for Yosemite Falls and housekeeping, we used a relative simple Bouguer anomaly to estimate the depth to basin gravity, and that's because the signal was farther away from the cliff faces, and so there was less noise. When we did the El Capitan and North Pines transects, we had to use a complete Bouguer anomaly for the depth, and when we did that, our complete Bouguer anomaly for the El Capitan and North Pines transect matched better with the Yosemite Falls and housekeeping simple Bouquet anomaly. You can kind of see that here, how we even have like a depth profile where it kind of looks like a basin for all of them. So the yellow is El Capitan, and then the gray is the North Pines, which are the two transects on the outside. And then we had our Yosemite Falls, which is the blue, and the housekeeping, which is the orange. We used a large basin density of 0.5 for contrast. And as you can see, we found the gravity predicted a depth of about 1,078 meters below from El Cap. And then the shallowest was around Yosemite Falls at 475 meters. We then did some deep Remy some deep REMI analysis as well. All those arrays were relatively short, and they were too short to see what the predicted complete depth near El Capitan would be. We only really analyzed the 3 transects, Yosemite Falls, North Pines, and El Capitan, and that's because our housekeeping array did not come through very clear, so we would have to redo it again. On here, the dashed orange lines shows a 600-meter depth shear velocity profile, and then the solid red line are the picks that we made from the fundamental made Raleigh dispersion curves, which is over here. Down here we have our LCAP, the 600-meter depth shear velocity profile, and then our picked velocity profile, and then we just kind of zoomed it in over here. These results don't necessarily validate what we found in gravity at the depth, but they definitely kind of support it. If we wanted it to validate what we found with the gravity, we would have to do a longer transect just because we don't have the ability to reach the basement because it's not good below frequencies of 1 hertz. And we would assume that we would get a rebound of a velocity of 3,000 meters per second. And we determined that from the Sierra Granite that a survey was conducted in South Lake Tahoe. And that's what it returned to them when they did that survey. So our conclusion is that the deepest part of the basin near El Cap has an estimated depth of 1,000, what the gravity claimed was 1,078, but it was plus or minus 215 meters. Our shallowest basin depth is near Yosemite Falls with, like I said earlier, an estimated depth of 475 meters. The gravity estimate basin thickness at housekeeping was 753 meters, which is similar to what Gutenberg estimated. In that original map, he's had that it would be, his deepest estimated depth would be 600 meters, and it's kind of near where that transect was. For LCAP, our gravity did estimate more than 3 times Gutenberg's estimated depth near LCAP. With all this information, it could be assumed that the aquifer may be thicker and could possibly provide a higher storage capacity, and you could have deeper wells in the valley. Ta-da.
We definitely have time for questions.
For your ambient noise analysis, what do you think are the sources of the ambient noise?
For the deep REMI, our ambient noise, we went to the valley to do deep REMI in August, and that's when the park is most full. There are tons of water trucks and buses running around, and there's tons and tons of people walking around. So it's definitely, the ambient noise definitely isn't as strong as you would say if you were in a city and there was like a freeway or a train running by, but we figured there's enough people and enough cars and trucks driving around that it would work out for us.
Other questions?
Did you see any evidence for the water table when you banked it?
For the water table? Not necessarily the water table directly. What we pulled was, you could kind of see it in our resistivity data. And LCAP, you can see like the pretty low resistivity over on the side here. But that's about really all that we really did to find the water table. We were just kind of trying to estimate and figure out what was happening below the surface. It definitely needs to have more research done to find the actual water table.
One more question?
Given the challenge with the terrain corrections, do you think it's worthwhile to collect more gravity data here, or is it?
I think it would be helpful to go back and also collect more gravity data, but also we did our outer ring corrections twice, and then we only did our inner ring corrections once. I think it would be helpful to do another our inner ring corrections by hand and do it out to 3 kilometers. Just because the DEM file we use, the GTOPO 30, is definitely not as intricate as it should be for that small area in the valley.
Okay, I have one question. So for your deep Remy, you say the transect was too short, but it was still over about a kilometer. So how much more would you expand it if you wanted to use this method there?
If we were to go back and do this method, instead of doing it north-south, I would like to do it from east to west and figure out how to do one completely through and then a few longer ones, maybe kind of staggered throughout the valley to kind of like fit into the snake pattern of that.
Why do we supposed to do the DC method? Like why the draw boxes to the depth measure? So why do the method?
So the question is, what purpose did the DC resistivity surveys provide? What was the purpose, knowing that the bedrock was probably so deep?
For those shallow methods, that was just to kind of validate what we were getting with Gutenberg, because he didn't go as deep, and it was also to possibly find where the water table was. That's why we did the shallow methods, and to just kind of possibly match what previous work was done here.
All right, thank you. Okay, our next speaker, I have a paper for our next speaker. Is my next speaker here? Seidel? All right, you guys, we're going to have to take another break. I guess our next speaker is not here. So the last talk will be at 9:45. I do have the talk for that person here, Mr. Abila. Are you here? Abila? 9:45. Okay, we're going to go ahead and get started here in a moment. I'd like to introduce our next speaker, Hana Abila. From Texas Tech. She's going to be talking to us about DC resistivity investigation of a West Texas playa lake. Welcome, Hannah.
Good morning. My name is Hannah, and I'm going to talk to you about West Texas playa lakes. The primary goal of our research was to investigate the West Texas playa lakes and how recharge is important. Here on the left, we have the long-term mean annual recharge rates of the High Plains Aquifer. Majority of the low recharge is in the Oklahoma Panhandle and parts of Kansas. And over here on the right, we have the water level changes of the High Plains Aquifer. The hot colors show decline, which is majority in the South High Plains. Oh, God. This slide shows why playas are so important to us. Each blue dot represents a playa lake in the southern high plains. They are almost continuous. Over here, each blue dot shows a playa lake in the Lubbock area. There are over 20,000 playa lakes in this area. This is another reason why recharge is so important. Here's a map view of the playa lakes that we investigated. It's one whole playa lake, but there are 2 playa lakes into it. There's the western one and the eastern one. We took resistivity and seismic data along this red line. The western lake has a more round basin, while the eastern playa lake is smaller. The western one holds 4 times more water than the eastern one. At the yellow line, we had a soaker hose that was buried underground, which we used as an infiltration test to soak the ground. We did this right before our 3rd data set. This box and this box are 2 homemade infiltrometers that we made and buried into the ground. We usually soaked about 2 feet of water in each of these before our data set. The main method we used was the dipole-dipole array. We had a distance of 5 meters in between. The blue ones are the current, the red ones are the electrodes. We moved the red ones at a 5-meter spacing 5 times till n equals 6. After this, we plugged in our data to this formula. These are some of the materials we used. We used a homemade power source of 215 voltage connected to a switch box that controlled the current, also connected to 2 voltmeters with some wires and some electrodes. What isn't shown is the homemade infiltration box that we made and buried into the ground. Right here, we have a cartoon cross-section of the playa lake. Here's the watershed. Here's the water table. Here's the bottom of a playa lake, which is probably clay. And surrounding the playa lake, we have a caliche. And caliche can work as an aqualute, slowing down the water. Here are different pathways of the playa lake. We have mud cracks or fractures, basin floor, or an annulus. We're mainly worried about A through C. Here are some average rainfalls versus the months when we took our data. The first time we took our data was on March 15th, which occurred right before some rain, so it was relatively dry. The next data we took was on 4/25, which happened right after almost 2.5 inches of rain, and we flooded our box with 2 feet of water. The last data set was taken on May 3rd, after heavy rain and flooding the boxes. Here we have at the top our observed apparent resistivity, and at the bottom we have our 2D inversion. As you can see, the blue-green transition is probably the bottom of the playa lake, which is clay. There aren't very many blue dips, meaning that there wasn't really infiltration or anything unusual. We only made it through about the eastern playa here because it was our first day. And over here you can see some conductivity, but we didn't go past there to do some data over there. Here we made it through both playas, and as you can see, it's still relatively flat except in 3 spots. One spot, you can see that the conductivity decreased at the interplaya annulus. The other 2 are at our infiltration boxes that we soaked with water. You can also see that same conductivity annulus over here, but unfortunately we did not get our data over there. Here's our last data set. This is when we had about roughly 2 inches of rain and we soaked the box with 2 feet of water. As you can see, the rain did not affect the playa overall as much as we thought it would, but we still have infiltration of the annulus here between the playas and at our infiltrometers. We also took some seismic data of this land with a homemade thumper that we made. And my other research team are presenting their posters at 1 o'clock in the poster room. And as you can see, that the rain did not affect the playas as much as we thought it would, but when we soaked it and had a water hose leaking for several days, it actually did affect the data. We assumed that it went through mud cracks and that it infiltrated the annulus and created some conductivity. That's all.
Well, we have plenty of time for questions.
Oh, God.
Any questions? Well, while you're thinking of a question, I'll ask one. So why did you choose the dipole-dipole array over like a Schlumberger or a winner array?
We felt that it would show the playa overall better. He's raising his hand.
Our room after the rain event
Our first data set was taken on March 15th, and our second data set was taken on 4/25, or April 25th.
How long after the rain?
Oh, about a week.
But that's how long it took for the ride.
Yeah.
What do you think would be the relationship after later? What would be the different measures?
Well, basically, after the rain, it took a week before the ground was dry enough to walk on. And so, really, in terms of the soaking event, it was still soaked that entire week because it was standing water with fire until it went down.
So your minimum electrode spacing was 5 meters, is that right? So do you think that maybe might have been too coarse an electrode separation to see the fine scale changes in saturation near the surface of the playa?
No, I think it was a good separation because we saw pretty much like the main and the water infiltrating at certain areas.
Any other questions? Okay, thank you. Okay, everybody, thank you. That concludes our session. I appreciate your patience waiting for the various talks with our withdrawn speakers and no-shows. Hope you enjoy the rest of the conference.